Cool. Welcome back, everyone. Welcome to this track, everyone that was not here before. Thank you very much for joining us. Thank you, everybody online, for joining us. For the next talk, we have Dave Aronson, who has the coolest professional title that anybody has dared put on a slide today, T-Rex Codosaurus. And he's going to talk to us about how he plans or how we should kill all mutants or use the mutants, or I don't know.
Maybe
Please explain.
Both. Okay. Hallo Stockholm. Jag heter Dave Aronson, T-Rex på Codosaurus, och jag flög hit på min tama pterodactyl. There we go. För att lära er hur man dödar mutanter. Men jag kommer att göra det på engelska. Mainly because you've just heard almost all the Swedish I speak. So let's start at the very basics. What on infinite Earths is mutation testing? In our universe, that of software development, not comic books, excuse me, I mean graphic novels, it's a software testing technique. Surprise! But what makes this technique different from all the other techniques? Most of the others are about checking whether or not our code is correct. But mutation testing assumes that our code is correct, at least in the sense of passing all its tests. Oh, it's okay. Okay, instead, mutation testing is looking for two other properties. And in my opinion, the more interesting and important of these is that our tests are strict. Excuse me, the clicker doesn't seem to be working anymore now. I'll just do it manually. No, even manually does not seem to be working. Houston, we have a problem. Stockholm, we have a problem, whatever. There we go. Never mind. It just needs to get focused back on the thing. All right. The more important of the two qualities that mutation testing is checking for is that our tests are strict. Now, you may be thinking, isn't that what test coverage is for? If we have 100% coverage, doesn't that mean that our code is fully tested? No. The only thing that coverage tells us is that at least one test executed the code that shows up there in green to say that it is covered, and none of the tests executed the code that's showing up instead in red. It tells us nothing about whether the code is correct or not made any difference in whether any given test passed or failed. So let's look at a test and just comment out the assertion. Our test still runs the code, so it shows up as covered, but we're not bothering to do anything with the result, so it's obviously not tested. And this is just one of many, many ways that coverage can be very misleading. So how can we tell if the correctness of the code had anything to do with the passing or failing of tests? That is where mutation testing comes in. To check that our test suite is strict, a mutation testing tool will try to find the gaps that let our code get away with unintended behavior. Once we find these gaps, we can fill them in by either adding more tests or by expanding existing tests. Lack of strictness usually comes from lack of tests, of course, or poorly written tests or poorly maintained tests, especially if they just didn't keep pace with changes in the code. And speaking of the code, the other thing that mutation testing checks for is that our code is what I call meaningful. By that, I mean that any tiny little change to the code within reason will have a noticeable effect on the code's behavior. Lack of meaning usually comes from code being unreachable or redundant with other code, or just not having any real effect. And lack of meaning usually comes, excuse me, I already covered that. Once we find meaningless code, we can figure out why it's meaningless, and if it fits our intent, make it meaningful. In other words, remove the redundancy or whatever, or just remove it. That's usually fine, because if it's passing our tests and the code is meaningless, yeah, we can do without it. Mutation testing puts these two together by checking that pretty much every little change it knows how to make does indeed have a noticeable effect on the code's behavior, and that our test suite is strict enough to notice that change and fail. Now, not all the tests have to fail, but each change should make at least one test fail. Now, that's the usefulness of it, but there are some drawbacks. As Fred Brooks told us in 1986, there is no silver bullet, besides which those are for taking care of werewolves, not mutants. The first drawback is that it's hard labor on the CPU, and therefore usually fairly slow. We certainly won't want to mutation test our entire code base every time we save a file. Maybe over a lunch break for a small system, or a weekend or something for a large one. But fortunately, most tools contain ways to tell them to just check this function or this file, maybe this directory, which could still be huge, but out of a large system, that could be a reasonable slice. And most of them also, well, many of them also include some sort of incremental mode. There we go. So we can just tell it to check what has changed since last time we ran the tool, the last git commit, the change from the current contents versus the main branch in our repository, or some other such delta. That sort of things we can do maybe on every file save, or at least over a much shorter break than otherwise. Also, its CPU intensive nature can really run up our bills on cloud platforms such as AWS or Azure, however you pronounce it. And another drawback is that it's not at all a beginner-friendly technique. It tells us that some particular change to the code made no difference to the test results. But what does that mean? It takes a lot of interpretation to figure out what a surviving mutant is trying to tell us. Their accent is very strange, and they're almost as incoherent as zombies, with a much larger vocabulary. They're not always on about brains. They're usually trying to tell us that our code is meaningless or our tests are lax, but it can be very hard to figure out exactly how. Even worse, sometimes it's a false alarm, because the mutation might not make a test fail, but it might not have made any real difference in the first place. It can still take quite a lot of time and effort to figure that out. And even worse, sometimes, well, quite a lot of the time actually, it's a false alarm. Well, wait a minute, I already said that, sorry. Jet lag. Even if a mutation does make a difference, there's often quite a lot of code that we just shouldn't bother to test. For instance, if we have a debugging trace that says the value of X, the value of X is, and then the value of X, that constant part is, the value of X is going to get mutated, even though we probably don't really care about that. And we're almost certainly not going to write a test against that literal string. Fortunately, most of them have ways to tell it, don't bother mutating this line, this function, maybe even this whole file. But that's often done with comments and can make it a little hard to read and clutter it up. Now that we've seen some pros and cons, how does mutation testing work, unlike the guy in this sign? It mutates copies of our code, hence the name, and it does this with the intent of creating test failures, otherwise known as faults. So mutation testing can be categorized as a fault-based testing technique. And this means it's sort of related to something you might already be familiar with, Chaos Monkey from Netflix. Just like Chaos Monkey helps Netflix know that their error recovery is working fine, mutation testing helps us check that our code and our tests are fine. But the way mutation testing works is sort of upside down from what Chaos Monkey does. Chaos Monkey is best known for injecting faults into Netflix's production network. And if all still goes well, in the sense that Netflix's customers don't notice and their metrics still look good, then Netflix knows that their error recovery is working great. But mutation testing, instead of injecting faults, it only injects semantic changes. It doesn't know whether these changes will produce faults or not. Now, we hope they all will, but that's up to the test suite. It injects them into copies of our code, not our actual network. And it does its work in our test environment, not production. And if everything still goes well, in the sense that our tests all still pass, that does not mean everything is fine. That means that there is a problem. Remember, each change to the code should make at least one test fail. Mutation testing has also been compared to fuzzing, a security penetration technique involving throwing a lot of random data at an application. You might also be familiar with property testing, a very similar thing which has been discussed at this conference already. Mutation testing is somewhat like fuzzing our code rather than fuzzing our data. And it's also not random. Most tools have a set of mutations that they know how to do. It may seem random because it won't necessarily report on the results of each one of them. And some of the smarter ones can use the results from some simpler mutations to know they don't need to bother with some more complex mutations, but it's still not random. But enough about differences. What exactly does mutation testing do and how? Let's start with a high-level view. First, our tool breaks our code apart into pieces to test. Usually, these are our functions or methods if we're using an object-oriented language, but I'm just going to say functions. Then for each function, it tries to find the tests that cover that function. If the tool can't find any, most will simply skip that function. Better yet, most of those will warn us, so we know we need to go add some tests or annotate some. More on that later. Some, though, will use the entire test suite, which is horribly inefficient because it's running a lot of tests that aren't really relevant to that function. Now, assuming we're not going to skip the current function because of not finding tests or whatever, then the tool makes the mutants. And to do that, it looks closely at the function to see how it can change it. For each tiny little way the tool sees to change this function, it'll make one mutant with that one tiny little change. And once our tool is done creating all the mutants it can from a given function, then it iterates over the list. And now we get to the heart of the concept. This chart represents the progress of our tool. The tools generally don't give us anything so nice, neat, and organized, complete, often not even the data from which we could construct such a chart. But this is just a model that I use to explain the point. So for each mutant derived from a given function, the tool will run the function's tests, but running them with the current mutant instead of the original code. And if any test fails, this is called killing the mutant, and it's a good thing. It means that our code is meaningful enough that the tiny little change that the tool made in order to create this mutant did indeed have a noticeable effect on the code's behavior. And our test suite is strict enough that at least one test would spot that difference and fail. Then the tool will mark that mutant as killed, stop running any more tests against it, and move on to the next one. Once a mutant has made one test fail, We don't care how many more it might make fail, like perhaps some of mutants 6 through 10, tests 6 through 10 for mutant number 1. Like so much in computers, we only care about ones and zeros. On the other claw, if a mutant lets all the tests pass, then it is said to have survived. And this means that it has the superpower of mimicry, skilled enough to fool our tests. Now let's peel back one more layer of the onion and look at some technical details of how this works. First, our tool parses our code, usually into an abstract syntax tree, so that this code becomes this abstract syntax tree, more or less, depending how you represent and simplify it. And I'm going to assume that you're familiar with the concept of an abstract syntax tree, but we don't need to worry about understanding this particular one in detail. After the tool creates an AST out of our code, then it traverses the tree, looking for subtrees or branches, if you will, that represent our functions. After finding them, it handles them basically, like I said before, starting with looking for each one's tests. But how does it do that? That usually relies on us developers either annotating, there we go, annotating our tests, as I hinted at earlier, or following some sort of naming convention for the tests or the files, or perhaps both. These manual techniques are sometimes supplemented, occasionally even completely replaced by the tool actually looking for what tests call what functions. Anyway, after the tool has found the functions tests by whatever means, then assuming we're not going to skip it because we haven't found any tests, it makes the mutants. So how do you make mutants from an AST? It traverses that functions subtree just like it did for the whole thing, except now, instead of looking for even smaller subtrees to extract, like twigs or something, it's looking for nodes where it can change something. And each time it finds one, then for each way our tool knows how to change that kind of node, it will make a fresh copy of the entire subtree with that one particular node changed in that particular way. So suppose our tool had started traversing this function subtree from that AST I showed you earlier and has gotten down to this if statement. For each way that the tool could change that one node, it would make a fresh copy of this subtree with that one node changed in that one way. And as soon as it's done making as many mutants as it can by changing that node, it'll continue traversing the subtree down to another node, in this case, a child of that node. And again, for each way it can change that node, it'll make a fresh copy of this entire subtree with that one node changed in that one way, and so on until it has traversed the entire subtree. Now I've been talking about changing things. So what kind of changes are we talking about? There are quite a lot. It could change a mathematical, logical, or bitwise operator from one to another. In languages or situations where we can do so, we can change it into one from one of the other categories. For instance, in many languages, we can treat anything as Booleans. So X times Y could become X and Y, or X exclusive or Y. When the order of operands matters, such as in subtraction, division, exponentiation, or string concatenation, it can swap them. It can change a comparison from one to another. It can insert or remove a logical, bitwise, or mathematical negation. It can remove entire statements. And it can remove a condition so that something that might either be done or skipped over will always be done. In languages with looping constructs, it can also remove the conditional that controls a loop so that something that might be done once, done many times, or completely skipped over would be just done once. It can replace a function's entire contents with returning a constant, returning either of the arguments alone, raising a deliberate error, or nothing at all if the language permits. It could change a value to another value, such as any of these or many, many more. And I know some of those math constants don't really exist on the beam. They're just there for illustration purposes. It could even change it to something of a completely different and potentially incompatible type, like changing a number to a, if I may quote Smeagol, string or nothing. Someone got it. There are many, many more types of changes it can make, but I trust you get the idea by now. Now, from here on, there are no more low-level details I want to add. So let's peel back one more layer of the onion and look at some Elixir-flavored pseudocode. So about to say Lisp-flavored because I've heard so much about LFE past couple days. Anyway, some Elixir-flavored pseudocode illustrating how it works. I'll talk a bit so you can take pictures if you want. Never mind how it goes on to the next mutant or next function. That's part of why it's pseudocode. Doing this up in proper functional style with recursion and such, I couldn't make that fit easily on one slide. I don't see anybody still trying to take pictures, so moving on, let's finally walk through some examples. We'll start with an easy one. Suppose we have a function like this. Never mind why, it just makes a good example, so let's roll with it. Think what a mutant made from this might return, since that's probably what our tests would be looking at rather than side effects. This doesn't look like it would have any. Mainly, such a mutant could return results such as any of these. And again, many more, but I had to stop somewhere. Now let's suppose we have only one test like this. Now, that's a rather poor test, and I think why is immediately obvious to a lot of you. But even so, most of the mutants on that previous slide would get killed by this test, the ones shown here in crossed out green. The ones returning constants are very unlikely to match. There's no particular reason our tool would have the function return a 4 as opposed to 1, 0, -1, and so forth. The mutants that subtract one from another would just give us 0. Division gets us 1. Yes, and the error conditions will at least make the test not pass. But addition, multiplication, and exponentiation in the reverse order will still get us the right answer. So mutants based on those mutations would survive our test. So how can we actually observe this happening? When we run our tool, it'll give us a report that looks kind of sort of like this. The exact format and amount of context and so forth will vary enormously depending on what tool we're using, but the information semantically should be roughly the same. And what it's telling us is that if we change the function called power, which is in file demo.ex, starting at line 42, in any of 4 different ways, then all its tests would still pass. And then it goes on to tell us that those 4 ways are, first, to change line 42 to swap the arguments, second and third to change line 43 to change the exponentiation into addition or multiplication, and last to change line 43 to swap the operands of the exponentiation. So what is this set of surviving mutants trying to tell us? Now, the very high level message is that our test suite isn't very strict, either because we don't have many tests or they aren't very good, but we knew that. The question boils down to, how are these mutants surviving? The usual answer is that they return the same value or have the same side effect, if we're doing that, as our original function. To determine how that happens, it helps to take a closer look at one mutant and a test it passes. Let's start with the plus mutant. Looking at the change and the test together, make it fairly clear that this is surviving because 2 plus 2 equals 2 to the second power. And so does 2 times 2, but he's in the background. We can save him for later. So how can we kill this mutant? In other words, make at least one test fail when run against it. It's quite simple in this case. We just need to make one test, use inputs such that x to the y is different from x plus y. For instance, we could add a test or change our existing test to something like this, asserting that 2 to the 4th power is 16. All the mutants that our original test killed, this would still kill. 2 plus 4, however, is 6, not 16. So this kills the plus mutant. Better yet, 2 times 4 is 8, which is also not 16. We programmers know our powers of 2 at least that well. So it also kills the times mutant. You'll often find that killing one mutant has, perhaps you could call it, collateral damage of many other mutants. However, the pair of argument swapping mutants still survive. But that's okay, we can attack them separately. No need to kill them all in one swoop and be some kind of superhero about it. To kill them, again, we can either add a new test or change our existing tests to something like this and assert that 2 to the 3rd power is 8. 3 squared is 9, not 8. So this kills both of the argument swapping mutants. And better yet, 2 plus 3 is 5, 2 times 3 is 6. Both of those are not 8. So the times and plus mutants stay dead, and we don't get any zombie mutants wandering around, even if this were still our one and only test. So with these inputs, the correct operation is the only simple common one that gets us the correct answer. Now, this isn't the only solution, though. We could have used 2 to the 5th, 3 squared, vice versa, and infinitely more. There are lots of ways to skin that flurkin. Now, this may make mutation testing sound simple, but this was a downright trivial example, so we could easily think up ways to make all mutants, within reason, return a different answer from the original function. So let's look at a more complex example. Suppose we have a function to send a message like this. This function, send message, uses send bytes to send as much as send bytes can handle in one chunk, and then recurses to pick up where it left off. I've seen this sort of pattern, though with usually loops rather than recursion, used many, many times in communication software. Now, a mutation testing tool could make lots and lots and lots of mutants out of this, but one of particular interest would be this, an example of removing a statement, removing those lines with the minus signs. That's what they mean. Now, suppose that this mutant does indeed survive our test suite, which consists mostly of this. There's a little more that I'm not going to show you quite yet, dealing with setting the size and actually creating the message. But even without seeing that, what does the survival of this non-recursing mutant tell us? If a mutant that only goes through this function once behaves the same as our regular code, as far as our tests can tell, that means that our tests are only making this function execute once. So what does that mean? You'll find that interpreting mutants involves a lot of asking yourself, so what does that mean? Often quite recursively. In this case, it means we're not testing with sending a message larger than send bytes can handle in one chunk. There are lots of ways that that could happen, but most likely we just need to use a bigger message. For instance, here we see our maximum chunk size for send bytes is 10,000 bytes, and yet we're only testing with an itty bitty 3-byte message. Maybe 4 if we have a null terminator, or maybe a little more depending exactly how it's serialized, but almost certainly not 10,000 bytes. And the obvious fix in this case is to use a bigger message, bigger than we can send in one chunk. And it's easy to construct one with this pretend code. We just take our maximum chunk size, add 1 or however many we care to, and create that big a message. But maybe we did test with the largest permissible message out of a predefined set of either messages or at least message sizes. For instance, here we have small and large message sizes. We tested with a large, and yet this mutant still survives. What could possibly be wrong with that? What is it trying to tell us in this case? Now it's trying to tell us that a version of send message with the recursion removed would do the job just fine. If we remove the recursion, we wind up with this. And I think that makes it fairly clear what the ultimate message is, but we'll go through a couple more steps. We'll probably get some compiler warnings out of this. So let's do away with the unused parameter and assignment. And that should make it extremely clear that the ultimate message is that send message may well be redundant, and we can just use send bytes directly. Now I say may well be redundant rather than is redundant because in real world code, there might be some logging or error handling or whatever that we need to actually have in send message. But at the very least, the recursion was redundant. Fortunately, when it's this kind of problem with unreachable or redundant code, the solution is clear and easy. Just rip out whatever it was that the mutant doesn't have. That'll also make our code more maintainable by getting rid of useless cruft that just gets in the way of understanding. And now that we've seen a few different examples of spotting bad tests and redundant code, I'd like to address some occasionally asked questions. Mutation testing is still rare enough that I don't think there are really any frequently asked questions. First, this all sounds pretty weird. Deliberately making tests fail to prove that the code succeeds. Where did this bizarro idea come from in the first place? Mutation testing has a surprisingly long history, at least in the context of computers. It was first proposed in 1971 in Richard Lipton's term paper titled Fault Diagnosis of Computer Programs at Carnegie Mellon University. The first tool didn't even appear until 9 years after that in 1980 as part of Timothy Budd's PhD work at Yale University. Even after that, it was still not practical for most of us with consumer grade machines or even a little better than that until maybe the past couple decades or so with improvements in CPU speed, multi-core CPU, larger and cheaper memory, and so on. And that leads us to the next question. Why is it so CPU intensive? Now, to answer that, we have to do some math, but don't worry, it's fairly basic. Suppose our functions have on average about 10 lines each, and each line has about 5 places where it can be changed to any of about 20 alternatives. That works out to 1,000 mutants per function. And for each one, we'll have to run somewhere between one of the function's tests if we get lucky and kill the mutant on the first shot, all the way up to all of that function's tests if we kill it on the last shot, or worse yet, it survives. Suppose we wind up running just 1/10 of the function's tests on average. Since we start with 1,000 mutants, that's still 100 times as many test runs as just normal running our test suite. So if our test suite normally takes a zippy 10 seconds, mutation testing will probably take about 1,000 seconds with these assumptions. That might not sound like much because I'm saying seconds, but do the math and it's almost 17 minutes. And the last question is, when making a mutant, why change it in only one way? There are multiple reasons. First off, the main theoretical underpinning of mutation testing is the competent programmer hypothesis. So let's give that a quick check. Raise your hand if you're competent. I'm not seeing a lot of hands out there. Maybe you're still having food coma from lunch, or maybe you think you're not competent. Okay, go read up on, imposter syndrome. But anyway, what is the competent programmer hypothesis? Long story short, it's the general idea that we usually have a pretty good clue what we're doing most of the time. And when we make a mistake, it's usually one small mistake, like a typo or adding when we should subtract, or comparing things with less than or equal to when we should be doing strictly less than or maybe greater than or whatever. Does this kind of simple substitution sound familiar? Yes, it's exactly the kind of thing that a mutation testing tool does to your code. So you can sort of think of mutation testing as a did you mean function, sort of like when Google says, did you mean search for this other thing that might have a little more hits than what you were looking for? There are also practical considerations. For one, it helps us poor humans focus. It's much easier to tell what a surviving mutant is trying to tell us if we were only talking about one thing in the first place. Another reason is that multiple changes may balance each other out, leading to more false alarms. Like if a single mutant had both of those argument swapping mutations, one would swap the arguments and one would swap them right back for no net effect. Allowing multiple mutations would also create a combinatorial explosion of mutants, with our tool making orders of magnitude more mutants per function, which would make it even more CPU intensive. To summarize at last, mutation testing is a powerful technique to ensure that our code is meaningful and our tests are strict. And it's easy to get started with in terms of setting up the tools and annotating our tests if need be. Maybe tedious, but at least it's easy. But it's not so easy to interpret the results, nor is it easy on the CPU. Even if these drawbacks mean that it might not be a very good fit for our projects at the moment, I still think it's just a really cool idea in a geeky kind of way. If you'd like to try mutation testing for yourself, here's a list of tools for some popular languages and platforms and some other ones. I doubt many of you are doing Fortran 77 these days. I'll talk a bit more so you can take pictures. Just be aware that many of these are outdated. I don't know or follow quite all these languages and platforms, let alone the tools. The ones I know are outdated are crossed out. There's also a promising tool called Wodal Test, which is a language independent mutation engine with which you can make language specific mutation testing tools. Sorry, I haven't actually played with it myself. For Elixir and Erlang, there is a fairly recent one called Darwin. I have not tried it. For Erlang, there's also Mutu or Mu2. I have no idea how it's supposed to be pronounced. For Elixir, there's also Xavier, X-Men Mutation, and a more recent one called Muzak. Everybody done taking pictures? Okay. Before we get to Q&A, I'd like to give a shout out to TopTal, a consulting network I'm in that has a speakers network that helped me prepare and practice this presentation. Please use that referral link if you want to hire us or join us, because that anchor tag tells them it's me. And also many thanks to Marcus Sherp, creator of Mutant, the main tool I've actually used. It's for Ruby. He's also been very willing to answer my ignorant questions and critique the original version of this presentation. So now it's your turn almost. If you have any questions, I'll take them in just a moment. If you think of anything later, I'll be around for the rest of the conference, even though that's not much time. And if you think of something later, there's my contact information, or you can just find me through Whova or whatever. And there's also the URL where you can get the slides complete with script, which I've wandered from a little bit, and some bonus material. So any questions?
Do we have any questions? I haven't seen anything on Whova yet.
Right. Anything from online?
I can check again. Otherwise, I can perhaps take a shot. So how long have you been using these techniques yourself? And what's your experience with this?
I haven't actually used it very much. I've done a lot more reading up on it than actually using it, I must confess. But that started probably about 5 or so years ago. I had heard of it longer ago, thought it was a really cool idea, and then finally got an opportunity to try it on some projects at work. And yeah, I gotta say, the hard part is figuring out what a mutant is trying to tell you and then what you need to do about it.
Hmm.
It can take quite a while for the testing run to finish, especially if you're on a fairly weak machine like a MacBook Air or something, as opposed to big honking server. But once that's done,
Anything
you can-
particularly egregious that you have seen? Like, have you ever seen a mutant that was terrifying to survive in your code?
any terrifying surviving mutants, you mean?
Yeah.
Well, I've seen some terrifying code, but I don't think I've seen any that were in the form of surviving mutants.
More
If
questions?
there's no others, then I guess we get about 3 minutes of our day back.
Yes. Thank you very much again, Dave.
Thank you.